I have divided the lecture into two parts. The first one that I have here, we're going to be making the aldehydes and the ketones. And the second one's going to be a little longer. It's going to be the reactions of the ketones. So we're going to make aldehydes and ketones, and a lot of these reactions are a review of things that you have learned before. Like, for example, if you have a primary alcohol, we can oxidize the primary alcohol to the aldehyde by using PCC. PCC stands for pyridinium chlorochromate, and we get the aldehyde out of that. If you happen to have a secondary alcohol like the one that we have here, the other chromium 6 reagents work better. So the chromium trioxide or the potassium or sodium dichromate work perfect. When you use those two, you use them in sulfuric acid, so you're going to see them together. And the secondary alcohol can only be oxidized to a ketone. So there's not much that we can do with a secondary alcohol, so you don't have to worry about it. Even if you use PCC on the secondary alcohol, you'll still get the ketone. But if you were to use any of these chromiums with your primary alcohol, that would be a problem. You would get a carboxylic acid out of this. So primary alcohols with PCC give you aldehydes. Secondary alcohols give you ketones with any oxidizing reagent. This is an old reaction that you know that I like a lot, and it's the ozonolysis reaction. So the first step of the reaction would be the reaction with ozone. And the second one is going to be reductive conditions. So we're going to use dimethyl sulfide. And what that's going to happen is that we're going to break the double bond in two. We are going to separate the double bond. We're not going to change anything that's attached to the double bond. It's going to stay there. I have CH3s and a hydrogen directly attached to the double bond, and we oxidize the carbon to the carbonyl. Now, these are reducing conditions, so I can get aldehydes and ketones out of this. The next reaction, we didn't see it that long ago. This is the Friedel-Crafts reaction, and we have benzene. And this is the acylation reaction. Remember that Friedel-Crafts they have two different reactions, the alkylation and the acylation, and this is the good one. So you start with an acyl chloride, benzene, and the catalyst aluminum trichloride. And what we're basically going to do is attach the carbonyl to the benzene ring. We don't do anything else. Nothing else happens in this reaction. Once you finish, the ring is deactivated, so it will not add a second carbonyl. All right, the next reaction you may not have seen before, but I'm going to teach it to you here. This one right here is an organocuprate, and notice that the copper is going to have two alkyl groups. It doesn't really matter what the alkyl groups are. One of the alkyl groups is going to take the place of the chloride. This chloride happens to be attached to a carbonyl, and that's why we're seeing it in this particular chapter. But if you have a chloride of an alkyl chloride, the reaction will still replace the halide for one of the groups on the copper. So I have a double bonded carbon, and I am going to replace the chloride for that group. So this is an organocuprate, and it's a more gentle organometallic. It will not attack the carbonyl directly. It will replace the halide for just one of the groups that it has on. Alkynes can be hydrated to get aldehydes and ketones. And this one is a terminal alkyne, so that we can see the difference between the Markovnikov and the anti-Markovnikov addition. All right, this one right here, we're adding water, sulfuric acid, and a little bit of mercury to make the reaction go a little faster. This is going to be a Markovnikov addition of water. And when we add water Markovnikov, the hydrogen is going to go to the carbon that has more hydrogens. So it's going to go on the outside carbon. So I have a hydrogen there already. I'm adding a second hydrogen, so now I have two there. and the oxygen goes to the other one. This is an enol, and enols cannot be isolated. Enols tautomerize to the keto form, to the carbonyl. In this particular case, I'm going to get 2-butanone out of this. And that would be the Markovnikov addition. Let me see if you can see it. There we go. This one at the bottom is the anti-Markovnikov addition. And I have my boron reagent. Remember that when you're working with a triple bond, you need to have two big groups attached to the boron. And then the second step is your basic hydrogen peroxide. But it's a Markovnikov addition, so the hydrogen is going to go to the carbon that doesn't have any hydrogens in this particular case, so it's going to go on the inside. The OH is going to go to the outside one. This is still an enol. An enol is a double bonded carbons, two double bonded carbons that have an OH directly attached to it. And the process of tautomerization favors, in this particular case, the aldehyde. So if you add water anti-Markovnikov to a terminal triple bond, you get an aldehyde. If you add the water Markovnikov, we get a ketone, but not just any ketone. It's a terminal alkyne, and this carbon at the very end just turned into a CH3, so it's a methyl ketone. All right, the next reaction you have not seen before, although I did teach it to you in class, but it's the oxidation of allylic alcohols. It's a selective oxidation, and only allylic alcohols can be oxidized this way. Now, allylic is a carbon that's directly attached to a double bond. So whatever's attached to the allylic carbon becomes the allylic hydrogen, or in this case, the allylic alcohol. And this is manganese dioxide. It's a good oxidizing agent. It's actually very selective because it's only oxidizing the allylic alcohol. And this one happens to be a primary alcohol. And manganese dioxide will oxidize that primary alcohol to the aldehyde. And that's important because we want, selectivity. If you happen to have two alcohols, let me just make up another molecule right here. Let's say that I still have, let's just put it right here. I have two alcohols in this molecule. This one on the left, this one is just a primary alcohol. This one, that's the allylic carbon, so this is an allylic alcohol. And that means that when I add manganese dioxide, only the allylic alcohol will be oxidized. So the primary alcohol that's on the left, it's going to remain untouched. And that primary alcohol is going to be oxidized to an aldehyde. The next reaction, and the last one actually, it's a reduction. And it's a reduction of an ester. This is an ester right here, and it's one of the functional groups we're going to see in the chapters that are coming. But notice that I have an OCH3 right here. This is a methyl ester, and I can actually reduce it with dival. Dival stands for diisobutyl aluminum hydride, and notice that I have a hydride. So I have the aluminum and I have the hydride, but I only have one hydride. It's like lithium aluminum hydride, but it has only one hydride. Notice that I still need two steps for this. But the important thing is that I can take an ester and react it with dival, and I can isolate the aldehyde out of it. As a matter of fact, if you had the acyl chloride, it will also be reduced to the aldehyde with dival. So dival is another one of those reagents that are selective, so we tend to use them in a specific way. This is the ending of making aldehydes and ketones. The next part is the reactions of aldehydes and ketones.